That I am. That I am. All right. So how was your weekend about to be?
Gaming.
Busy.
It's going to be grueling.
Grueling, yes. I've seen the T-shirts, by the way. I see some Firefox shirts. Any Game Jam shirts? A couple of Game Jams.
Firefox is game.
Yeah, you're getting in the spirit of things. Yeah, the new shirts are pretty cool. They had some interesting things.
Are they as good as the Firefox one?
I like the Firefox one. You know, it's that bright orange.
It's a nice neon dress.
It is, and you definitely identify the people that have Firefox shirts on in the class. Well, we have a lot to talk about.
Firefox was the last one.
So I did a couple of things in 3D graphics. We're going to try to condense this down into one lecture, which is almost impossible. I teach a lot of the 3D graphics classes here in OpenGL and such. So fortunately, doing 3D graphics in XNA is way easier than doing it in OpenGL. Has anybody taken the OpenGL class?
I want to.
No. Okay. So I think it's required of all games majors, right? You have to take graphics. So pay special attention to the overarching themes here because it's going to pay off a little bit later. That's a Reese's shirt, by the way. That's not Firefox. So, if somebody could close the door, I would appreciate it. Okay, so what I've done is I've broken the lecture down into 3 different phases, and we're going to kind of go through it relatively quickly, so my apologies. I wanted to talk about coordinate systems because that's one of the most difficult concepts, and it doesn't need to be. Everybody gets hung up on matrices and these kinds of things. And so we'll talk about that. I'm probably going to interject that partway through this 3D graphics right here when we get into that. And then also I'm going to talk about, I've got this dragon.fbx file right here. We're going to get that thing rendered in XNA so everybody can see what that looks like. We're going to drop back to XNA because it seems like that's what so many people are relying on. They said, the heck with the Vita, let's just go XNA because we know it. Anybody guilty of that? Yeah, okay, so a lot of people are. That's okay. So let's go ahead and get into it. I can't even spell XNA. Okay, so what do you know about computer graphics? They can be shiny. One thing that you should know is that they've gone through a major transformation. So if you're going to go out there and you say, I want to teach myself the field of computer graphics, I know what's going to happen is everybody's going to go out there like on this Bezier assignment. They're like, I'm stuck. What are you going to do? You're going to Google. Everybody Googles and they're like, okay, I'm going to find out. If you Google when you're looking for OpenGL stuff, chances are you're going to find the old way that OpenGL was done. Okay, so that's the first thing that I want you to be aware of. You should be looking into shader-based OpenGL or shader-based graphics. Okay, the reason I say that is because all of the examples that I've seen are really old. I have an OpenGL channel. If you're interested in learning OpenGL, I have several hundred subscribers to that channel. So if you're interested in learning that, then that's an option for you. Okay, so things that you probably have heard of. Rendering is the process of making the image, right? So that process is there. A vertex is a single 3D vector, right? So this could be a position or it could be a direction and that kind of stuff. But a vertex is a point. Okay, an edge is a line between those two vertices. A face is what?
It's a box formed by edges of vertices.
For this class, it's going to be a triangle. Okay? We're not going to have even a square. We're not going to make it that far in this class. Everything in this class is going to be a triangle. Do you know why it's going to be a triangle? That's the only thing that's supported nowadays. So you don't have anything that's square. And the reason is because if I had a square and it was like this, 0.1, 0.2, 0.3, 0.4, and my apologies to the online students there, what would happen if I twisted this?
It wouldn't work.
Would it still be a square?
It would be 2 triangles. Probably.
It would be 2 triangles, and which way would the normal be facing? You know what the normal is, right? The normal is, we've talked about this a couple of times, it's a thing that's perpendicular to the plane. So if all of a sudden I start twisting these things, what's the problem? Yeah, what's the normal now? So it gets all screwy, and that's why a lot of these languages have only supported triangles. And so we're going to keep that in mind. Right, so it's a relatively simple kind of thing. You can do all sorts of interpolation, and we'll just move on. Okay? So the graphics pipeline overview. This is how graphics are actually rendered. It follows these 4 major phases. The first one is vertex processing. And so again, what's a vertex? It's a point inside your mesh, right? Whatever you're going to render. Okay, so what happens is we're going to do a lot of coordinate transformations into something called clip space. Don't worry about that right now. Don't really care. And we may also compute a pixel, a color for that particular vertex. Not the pixel. We'll get to that a little bit later. Okay, What happens if stuff falls outside of the screen? It needs to be clipped, right? Not everything is visible inside of a game. And so there's another phase that says what's visible and what's not visible. And then also we're going to assemble all of these little triangles. Right now we have a whole bunch of points that have been spun around. So you can think of it as like a point cloud that's been made. Now we actually have to make triangles out of all those points. You guys have all done connect the dots, right? And you know how you go 1, 2, 3, 1, 2, 3, and that's exactly what this phase does. Does this sound like a test question?
Yes. Probably.
Yeah, that gets people's attention. They're like, oh, class has just started. Do I have to pay attention? Yes. Get into it. Okay, so vertex processing is just moving the points where they need to be. And so right now you don't have anything visible. You just have a whole bunch of points that are there. Clipping and primitive assembly. That says things that are visible, things that are not visible, but the assembly is where the triangles are made. Does that make sense? Okay? Next phase after that is rasterization. You have no control over what happens here, but what is rasterized graphics? You need to know this term.
Rasterized?
Many of you are too young to appreciate video games of old. And I say of old, like back in the early 80s, late 70s, that kind of stuff. You know what I'm talking about. If you played a game back then, they had vector-based graphics. Now, we have vector graphics now, right? It's not the same thing. We had a vector monitor back then. Does anybody know how this thing worked? It was one of the most beautiful things you would have ever seen. Okay? Do you know what a CRT is?
Yes.
Most of you are old enough to remember TVs that work, the flat screen monitors and all that kind of stuff, right? How did those things work? You had a whole bunch of phosphors that were on the screen, which were essentially pixels, right? Then what would happen?
It would project onto. Wouldn't there be like essentially something at the back of it?
There is a ray gun, I kid you not, and I'm surprised that we're not all dead from this thing, but it was this electron ray, and it would scan across, and it would shoot energy at these phosphors, and it would make that phosphor light for just a fraction of a second, and then it would come back up, and it would draw the next thing, and there would be red phosphors, green phosphors, and blue phosphors. And I remember being a kid and going up really, really close, and I could see all of the individual colors that were there, and then I back up, and all of a sudden, voila, you can see the whole thing. It was like magic, right? That's the way that these vector games worked, except they didn't have color. You know what they had? Just phosphors. Like the whole thing was covered with phosphor, and this would actually trace the outlines of all the shapes that needed to be on there. Now, why was this so cool? Because it was continuous, first of all, but they could leave the beam in one spot a little bit longer than the other spots, and what would happen?
Make it brighter.
It was so bright it almost hurt to look at it. So I remember seeing like these little aliens and stuff come across, and this light would come across that would be painful to look at. Guess what?
Sun.
They're now coming out with monitors that have that benefit too. So that I've seen these things too, and it's amazing. When I say black, it is pitch charcoal black. It looks like it absorbs light. And when it's white, it almost hurts to look at. And when I said, how much, this was several years ago, I said, how much does that monitor cost? And he says, right now? I said, yeah. He said, about $100,000.
What? Start saving.
Start saving now, right? But these things are coming out. We know these as HDR, right? The high dynamic range kinds of things. But anyway, so the rasterization is taking all of this stuff and fitting it so that we can draw rasterized lines across the screen, right? So we're breaking it down kind of into individual pixels. And then finally, we have fragment processing. You can think of this as where the pixels live, and we give these things a color. Okay? So the rasterization is determining which pixels are on the screen that need to be lit. And then finally, this fragment process is determining the color. Does that make sense? Those are the four major phases of the graphics pipeline. You need to know them. Okay, and then we have coordinate systems, and this is where the confusion usually starts. All right? We had talked before about how the 3D graphics pipeline sort of works in terms of you have artists and you have programmers and these kinds of things. What typically happens if I'm going to make a 3D game? You have an artist. What do the artists do? They make a model. With me? You make it in Blender, you make it in Maya, 3ds, something like that. Then what happens? We pull that into Unity, but there's magic that's going on. There's a whole bunch of matrix math that's going on under the hood. Watch what's going to happen. We have a couple of different matrices that you're going to see in your next assignment after this one. Or is it? No. No, flocking is next. Then the 3D graphics is after. But it's coming. It's eventually, right? You have object space. This is the space when the object is modeled. What are we talking about? Blender, Maya, something like that. Okay? We also have world space. Okay? This is the game space where everything lives. So if you think of a virtual environment, something like that, you would say that tree is over there at position 10 over 10 this way or something like that, right? That's world space. That's with regard to the environment that we're creating. And then you have camera space. And this is the part that freaks everybody out. Okay? Believe it or not, when you're walking through a virtual environment, you're not walking. The world is moving around you.
Oh, so just like in 2D, when you have a side scroller.
It is. It's actually freaky. So if I were to sit here and I was walking towards you, do you know what really happened? The world was pulled this way. I stood still. Everybody else was translated. That's what's going on, because if you think about it, in graphics, you've got a first-person shooter, you've got something like that. Everything is relative to the camera. Does that make sense?
Yeah.
So if I were to rotate my head, I know everybody's thinking of this. I'm rotating. You are all moving. I'm not moving at all. I'm still at 0, 0, 0, looking straight ahead, but the whole world has just done this. Okay? So watch what we need. We need a way to get from this modeling space, this Maya space, to put them correctly into the world, and then we need a way to put that from the world into the camera space. Does that make sense? Let me say that again. We need a way to take this from one coordinate system, the Maya coordinate system, into the world space. There's going to be a matrix called the model matrix for that. Okay? And then we have to be able to put that into the camera space. Do you understand that concept? Because if you don't, you're hosed in this next assignment. Do I need to say it again? I will say it again, and I'll try to even shake it up and do something different. But you have to understand, I think everybody's cool with the spaces, right? You know what the Maya space is and the virtual environment space. We need a way to go between these different spaces. Yes?
So it's like parenting?
Think of it as a black box. It's not parenting. Parenting's a totally different kind of thing. But I need to say, okay, you're going from coordinate system 0, 0, 0. That's the middle of the, they were modeled at 0, 0, 0. We need to throw them at coordinate system 300, 300. In fact, do you see the confusion that's going on? Wouldn't it be cool if we had some slides that helped you with coordinate systems? Oh, wait. Here we go. In fact, I don't even care if we make it too much further through the graphics thing. We can come back to that. We've got a review that everybody said that they wanted. So we can come back. We have a little bit of time. I want to make sure these coordinate systems are comfortable, settled in your mind. Okay? There's not too many slides here, so let's just kind of get into them. Okay? So imagine that we're modeling this creature right here. I don't have nearly this talent. This was not me. I got this from Mixamo. Actually, at the last Game Jam, they gave out some credits, and so I don't know if you guys remember that. I borrowed some of those credits. Maybe I'll edit that out. But yeah, so I got this guy. Can you kill the lights real quick? Okay, so this is in Maya. I actually imported this into Maya just to see what it looks like. It's got these great textures and everything on it. But look at where the character's feet are. Where are they? They're at the middle of the universe, right? Yes, they are actually touching the ground. This point right here where these black lines are crossing is point 0, 0, 0. It's 0 high, 0 over, 0 deep, all of that stuff. Okay? So somebody spent time, and this is really important for us, because what we really care about is where this creature is, and when I do these translations and everything else, I don't want there to be an offset. Watch this. One of the problems that we're going to have is when this character is animated, what do they want to do? The animator wants to make the thing actually walk across the screen, right? Why is that bad?
Because we need to control the movement with our code, not
we need to control it with our code, not what the animator did. What we want to have happen when we have animations, and you guys all pay attention to this, when you're working with an artist and you say, I need some animations, they need to be centered at 0, 0, 0 at all times. I have people that are in Studio Capstone right now that are battling this, and they're like, oh, well, you've got to go back to square one now, kill the whole model because it's going to do you no good. Right? So all of the running sequences, everything, need to be like this sliding kind of thing where they're not moving at all, and then programmatically you move this character around in the world. Does that make sense?
Yes.
Yeah.
If it doesn't make sense, you just wasted $1,000. Think I'm joking? That's happened to me personally. Oh, do you mind going back and doing, oh, no problem. That's an extra $1,000. Okay. Oops. Okay, so that point is 0, 0, 0. I think everybody gets it. Then we have world space, right? So I took this character and I wanted to put him into Unity. And if you've ever messed with Unity, some of you have, you know that you can position these things around this virtual environment, right? So what we need is a way to go from that Maya space to now I want this creature to be at 619 over 10 down, 628 up, or whatever. It doesn't really matter, right? X, Y, Z.
You have a reminder.
On your shirt.
Oh, no. Okay.
Reminder, this.
Okay, there is clearly some funky key logging virus or something on here. Okay, so you now see the spaces, right? I'd like to be able to position this thing, and if I get more funky stuff on me, please let me know. I've actually had it appear on my head before when I was lecturing. Is Jeff possessed? But anyway, so I need a way to get them from this Maya space and put them into the world space. Agreed? Okay, so this is what it would look like from a top-down view. I want to position the creature right there in the world so that they can attack. Okay, so the question is, how did the monster get positioned correctly in the world? And we're going to come back to that. Okay, so then the third space that we're really interested in is this camera space. Does anybody know what this is? That is the main camera. That's the player, right? They're represented as a capsule in Unity, and it has a main camera that's on here. So you can see that the camera has moved around in the space as well, right? Right? No. Okay. So this is a convenience thing, right? This thing technically can move other stuff. So we have a separate matrix that's for the camera. And what that does is it puts everything back into camera position. So what are we really talking about? If I go to this next one, this is really what we want, right? Because the camera hasn't moved. The camera is at 0, 0, 0. You can see that. And where's the creature relative to the camera? 10 units pushed into the scene. So do you see what we've done? We've gone from Maya space, we wanted to then think in world space, but ultimately it comes back to camera space. Okay, so what if you want this camera to move through the environment? What are you really doing? You're changing the matrix for that camera just to pull everything else around the camera. That's kind of a mind-blowing thing. You're going to be walking down this hall and you're like, I'm not moving. SPSU is moving around me. Yeah, so don't think about that too long. It's really not that important. But this is what we're trying to do. Okay, so we have to get into the matrices at this point. Fortunately, in XNA, that's a very straightforward process, but you have to understand what's going on right here before we get into that. In fact, so here's what's going on. Going from this space to this space to this space, and how do we do that? We have a model matrix. This is sometimes called the world matrix. And it's going to take us from this space into this one. That's one matrix, right? A 4x4 matrix that we've studied. Then we have this one too, the view matrix. This takes it from the world space into the camera space. So we need two matrices. Now realize that this M matrix, you have one of these for every creature that you have in the scene. Whether it's a tree or a bullet or whatever it is, it doesn't really matter. Everybody has their own model matrix. What about view matrix? Why is there only one?
Because there's only
one camera.
What happens when you have two cameras, though?
Oh, stop. You're getting into all this. That's academic, esoteric nonsense. Yeah, but
if the player has two viewports, like what if you have another camera that you put separate?
oh, come on. Okay, you're right. Whatever. Oh. Okay, so a lot of times what we'll do is we'll combine these things into something called the model view matrix, right? It's basically the same thing. Technically, you could ditch the concept of the view matrix if you wanted to. That's not what I would recommend. Okay, so we talked about matrix. Do we want to get into this? I think we've done that. I'm not going to go back over all of this stuff. Yeah, we'll skip all of that. Hey, well, there you go. Yeah, we'll skip that for now because we're going to cover that a little bit later. Yes?
What about things like multiplayer games?
Multiplayer games. Think about that. That's a good question. Right? So if you do have the, let's say, picture-in-picture kind of view or a rear-view mirror or something like that, do you have two views?
Yes.
Two view matrices? Yes, absolutely. Why? You have two cameras, right? And that is an exception to the rule. Or if you have multiple cameras, do you really have multiple view matrices? So let's say you have a cutscene. You're viewing it from right here, and all of a sudden you jump over here. You may have two different data structures that hold that, but there's only one that's really active at a time. So that's a borderline case. Yes?
What about stereoscopic view?
Yes, stereoscopic view. That would be two. Yeah. What if you had a third eye? I mean, these are all great things, yes. But you get it. I'm glad. These are great kind of questions. All right. So how about this? Do we want to get into XNA now? Because, I mean, we talked about coordinate systems. let me show you something real quick here because this is going to tie into the code also. There's two different ways. The last thing that we need to worry about. We had the model matrix, right? And that takes us from Maya space into world space. We had the view matrix, which takes us from world space into camera space. Everybody, I think, is clear with that now. Okay? We have one last problem. Objects that are further away should do what? Shrink. They should get smaller. Okay? So there's one last matrix called the P matrix, which is the projection matrix. Okay? And it gives us these kinds of effects. Now, we have two different flavors of this. We have an orthographic view, and we have a perspective view. Which one do we want to use? Perspective. That means that objects are going to get smaller as they go further away. So up here in the upper right of this, you can see that all of these things are all the same size. All of these spheres are the same size. But depending on our view, this upper right one, you can see the ones that are closer are larger and the ones that are further away are smaller. Somebody had a comment?
They're scaled. Are they scaled?
They are scaled, actually, based off of their distance. Okay. But fortunately, we don't have to worry about constructing these matrices. So let's just get into it.
I don't know if that's what the orthographic function in Maya.
Oh, well, yeah, well, let's go back real quick. What is orthographic?
It changes it from that to where those other three options.
The question is, why would we ever want orthographic?
Well, if we're doing modeling.
If you're doing modeling, architects, you think of architectural plans, and you want to line stuff up regardless of distance. Right? So if you're trying to say, does this wall line up with the wall that's 30 feet down below and all that kind of stuff? Absolutely. You would want an orthographic projection. And they look like this. You can see that they look like a very flattened version of the space. Okay? So I could take this sphere right there and throw it back 3,000 feet, and it would still be the same size. Okay? So you guys want to see some code? Okay, so I'm going to come back to this and grab Dragon FBX. Hopefully, is this thing even set up, or is it going to ask me what language I want?
No, I don't think so. It wouldn't be malware on there if it wasn't already set up.
Yeah. Well, it's got some virus on it right now anyway, doesn't it?
Yeah.
Okay, and I may sit down for this because I'm pretty lazy. This is how you create a new project in XNA.
In case you've never done it.
And I'm going to save this on the desktop. And I'm not going to post this code, by the way, because there's something that I want you to do. This is a great dive into 3D graphics, right? So if you can remember the things that you're learning here, all of that's going to apply when you go into OpenGL as well. All right, so we'll select this. I'll call this thing Dragon Test or something, okay? So there's a couple of things that we'll want to do first. All right, so I have Dragon Test. It should be on this desktop here. Is it? Yes, here it is, okay? So watch what I'm going to do. The process is going to be very similar to what you've seen before. Right? I'm going to grab, here's my resource. And dragon.fbx is the Stanford Dragon. It's a very famous, iconic kind of thing in computer graphics. So I'm going to grab this thing, save the file.
Oh, the dragon curve?
The Dragon what?
Well, I was just thinking of the dragon curve, which is a mathematical dragon that's formed by essentially clicking the same pattern over and over. And so it always looks the same, essentially.
Okay, somebody help me out. Where is the downloads?
Yeah, arrow. Green arrow.
Okay, but I want to show in folder. Yeah, there you go. Okay, thank you. All right, so here's our Dragon. Here's Dragon Test. What do you think I should do?
Put it in the content.
How did you know I was going to put it in the content, right? So I take this guy, throw it over here. Okay, so there are my assets right there. I'm going to right-click, add an existing item. Here's Dragon. Add it. Okay? Now there's some interesting things. Notice, first of all, that I'm working with an FBX file. Let's talk about file formats. Why is FBX so good?
Small file size.
It supports animation. It's almost universally accepted. I mean, almost everybody uses FBX. And I know there's all these other kind of esoteric things, but FBX is a great format to be familiar with. Okay, so learn everything you can about FBX.
So can you rig animations and package it up?
This is assuming that it was done, like if you wanted to create something like this, open up Maya, and you can say save as FBX. Guess who created FBX? Yeah, Autodesk, right? So that's why it's supported, but it has support for just about everything that you need. And it's universally known. It works well in Unity, all of those kinds of things. Okay, so let me zoom in on the code so you can see some of this. Okay, I can click here on Dragon, by the way, and go to Properties. And there's a whole pipeline importing kind of thing that goes on. All right, so if you look here, see this content processor? I can drop this down and I could change this to say what kind of information that I'm working with. And then notice also here the content importer is an Autodesk FBX. Notice that it has all of these other kinds of things like an X file, sprite font. It has just a couple of different things. You can actually write your own custom importer if you have a proprietary format that you were going to work with. Okay, but for now the default is fine. Okay, so what do you suppose I'm going to need? Okay, texture. Somebody says texture. Is there a 3D texture? No, there's not a. Well, there. I think there is. But okay, believe it or not, there is a model. Okay, so I can say model, and I'll call it the dragon model. I don't know. Can you see? And maybe drop back some. I don't know if you can.
Yeah.
Okay, let me shrink this down here too because we don't need it. Can you guys see that? Okay. All right. Some other things that we're going to need are matrices, right? So let's have a model matrix. Let's have a what are the other ones? Okay, a view matrix and
Perspective.
yeah, perspective, or actually a projection matrix. There you go. Okay. So let's drop down here. I'm going to ditch this initialize. We don't need initialize. Okay. Load content. Is anybody else guilty of that too? You're like, the heck with this.
Yeah, that's the first thing I do when
It's an assignment, Jeff. Get over it. You know. Okay, so we have load content. Here, unload content. I'm going to kill that. We don't need that.
Oh, really? We can just get rid of them without any problem?
Well, remember, they're overridden and they're empty. So what's the harm in ditching them if you're not using them, right? So yeah, I just kill them. We'll just inherit. That's fine. All right, so what are we going to do? How are we going to load this dragon model? What do I say? Dragon model gets, no, not new. There you go. Content dot load. What are we going to load? A model. Okay, called dragon. There you go. You loaded a dragon model. How many lines of code would that be in C++? You do not want to know. Okay? There you go. So we've loaded the dragon model. Now the other things that we need to do are to initialize those matrices because we're going to have to pass those things off to the thing that actually does the matrix multiplication. We'll get there. Okay? So what I'll do is I'll say that the model is going to get matrix.create translation. Okay, what do I want to do? X, Y, and then Z. There you go. So what have I done?
Translate.
Yes, I did translate it, yes. Which way did I translate it? Into this. So this is the first thing. A lot of people are like, oh, I want to push it one unit in. So they put a positive 1 right there. Positive 1 is this way along the Z-axis, right? And it's this right hand. I see people doing all this kind of stuff. That's correct. It's a right-hand rule. So negative Z is the way that you would want to push stuff if you want to be able to see it. Okay? All right, the next thing is to create the view, but for now I'll just say that the camera is not going to move. Okay? And I see people still doing this. All right, so watch what I'll do. I'll say matrix.identity. What is the identity matrix? If I multiply by the identity matrix, what's going to happen? Nothing changes, and that's exactly what I want. Now, if you want, in the assignment, you have to make a first-person walker, yes? If you've looked at it, you know that you have to move through this environment. This is how you would do it. You would change the view matrix and do some of these translation things here. Does that make sense, right? Because the view, you're saying, I want to translate the whole world around this camera. So all I have to do is, for the view, say matrix.create translation and pass it the position or the inverse of the position of where the camera is going through this world, and then you're going to get this simulation of kind of walking through. Does that make sense? There's a little trick to it, but I'll show you that part a little bit later. Okay, so we now have the view. What about the projection? Projection gets matrix.create perspective. Oh, wait, hold on. Create perspective field of view. Now, notice this thing has a couple of different weird parameters to it. It's a little bit small for you in the back, but it says, I need a field of view. What's my field of view? 90. It's in radians. Crap.
Pi over 2.
Pi over
2.
no, it's pi.
Over 4.
Pi over 4.
Pi over 2.
I'm sorry. Pi r squared.
How about this? I'll just put in a 1.5. That's good enough for me. Okay. The next thing is the aspect ratio, and again, this is the dimensions of the screen, right? So what are we going to plug in here? 16 by 9. Sure.
4 by
The
3.
dimensions on the.
I think, yeah, you can get it, but it's roughly 800 by 600. It's like 9, I don't even know, but it doesn't really matter. So watch what I could do. I'm just going to hard code that for now. 800.0f divided by 600.0f. Or you could do that math ahead of time and put that number there, whatever, 1 point something, okay? What's the next thing in the list? It says the near plane and the far plane. Now, we need to have a discussion about this. We're going to see this later in the discussion of the lectures. But the near plane is the distance of where things are going to get cut off. If stuff gets closer to you than the near plane, it's not rendered. Let's have a discussion as to why that's so important.
So you can
You've seen it in games, right?
Yeah.
When does it happen?
Get really hard really something and you flip into like a wall.
Why is it so important then?
Because it saves processing power. You don't have to render
that, and you don't like get the whole camera blocked.
You don't get the whole camera blocked. It's to save the player, right? Because imagine that you're in this really tight space and you can't see anything. You want to give them a little bit of a distance so that they can see further in the game and kind of have an idea about where they are. Okay? So what we'll do in this class is we're just going to set the near plane to be 0.1, meaning that anything that's closer than 0.1, 0.09, would be clipped. Right? It's going to be culled out during that second phase of the graphics pipeline. Okay? The next one is the far plane. And this one's interesting too. What does the far plane do? Stuff that's further than that distance is going to be cut out also. Now, all of you have played some kind of RPG or something like that, and you're running through the desert, and what do you see?
Tree pops up.
A tree pops up. Hey,
desert?
that's weird. And you're running, and all of a sudden you can see the mountains being made as you run.
I think you're talking about Minecraft.
I'm not talking about anything, but you've all seen it in these games. Why? Because this far plane. So in real practice, how do they overcome this? Think about you've got this vast extent that has a lot of polygons, but you don't want to render all of those polygons. So you cut the near plane. What do? Skybox, you get that for free anyway. Somebody said it. Fog. Fog. Have you ever noticed, especially a lot of the earlier games, are like, oh, the heck with it, let's just throw in some fog. They do it all the time, right? Because if you have a lot of polygons, think about it, you have to cheat. Especially if you have these very large Sahara plain desert kinds of things, right? Because there's so many things that you would have to render. What they'll do is they'll throw in some fog. They'll throw in some wind that has some dust kick up so that you can't see that far plane effect. So for this class, what we'll do is we'll put it at 1,000, which is a pretty common kind of thing. Okay, there you go. Now we have something that is capable of making things get smaller the further away that they are. Okay, so we're almost done, believe it or not. So we'll drop down. We're not going to do anything in update yet, although we will in just a minute. We're going to come down here to drawing it. Now drawing it is going to be a little bit different. Okay? And the reason is because inside of a model, you can have several sub-meshes. Let me say that again. So when they create these models, what's going to happen is they'll create the arms separately, and they'll create the legs separately, and the head separately, and you're going to get all these body parts that are then combined in Maya. Does that make sense? Why they do that? Because they can mirror things and they can do all these kind of clever tricks. But you have to be aware of it, especially in the code. So watch what we're going to do. No sprite batch begin. Why not? We're not doing 2D, right? There's no sprite batches here. So what I'm going to say is for each...
Oh, really? Then what do you...
Well, here we go. That's a great question. Let me answer it. For each model in Dragon model, dot meshes, right? So that's saying for every piece that you have inside that thing, then for each basic effect, we'll call effect in model. Now I'm going to have to explain this one. These are the shaders. Okay, what we can do, we can apply textures, we can do all sorts of fancy stuff, but now I'm about to dig into the shader that's attached with that part. So imagine that I'm working with just the head part right now. It has its own shader. Now let's talk about shaders. What do? They move around the vertices, and they also color the thing. So watch what we're going to do. At a minimum, I'm going to say effect, effect dot, I think it's world. World gets, what do we call it, model matrix? Effect dot view, let me raise it up so you guys in the back can see. Effect dot view gets view. And effect dot, what is it, projection? Yeah, projection gets projection. It's been a while since I've done this.
You have conflicting variable names.
What?
Yeah,
Model.
It's supposed to be a model mesh.
Oh, yeah, the model.mesh. Thank you. Nope.
I think it's model mesh.
Or no. For each mesh?
Model mesh.
The word.
Oh, come on. Model mesh.
Still.
No?
Change to the model dot something.
Wait a second.
The model is the model matrix and the
Yeah,
models.
you have naming.
Oh, do I have them the same thing?
Yeah.
Yeah.
Yeah, just call it M.
Yeah, it's called all that.
Oh, that's right. That's it. Oh, there we go. M. Okay, for each end, there. Is that better? Will you stop complaining?
Maybe.
M dot something
M dot meshes.
for effects.
M
Effects.
effects. There it goes. Okay. Now, stop complaining. Okay, so let's walk through this code real quick. Probably for me, not for you. What we're going to do is we're going to walk through all of these meshes that are on the inside of the model. And again, this is the different pieces. But this basic effect is a pair of shaders. Okay. Basic effect there's two parts to it, and the one that we're messing with right now is the vertex shader. We're going to talk about this in just a minute, but the vertex shader is responsible for moving the vertices around in the environment. It's the one that's doing the matrix multiplication. That's why you see it right here. But effect is also a fragment shader, so it deals with lighting and coloring and all this other kind of stuff. So watch what I can do. If I were to run this right now, let's see, Shift F5. Okay, did it not take it? Shift F5. Fine.
It's just F5.
No, it's got a funky keyboard. It's got some special things up here. I see nothing. I'm highly disappointed. Cornflower blue. You're supposed to see an outline of a dragon. Let's see. World view projection.
You have to enable lighting.
Well, that's what I'm about to do. Enable default lighting. But I shouldn't have to. I was trying to get an unlit dragon, but I don't see anything. Why not? You know what?
Did you draw it?
No, I didn't. I didn't. Yeah, that's. I meant to do that. Here you go. Right here. M.draw. Yeah, see? Because if you don't draw, you won't see anything, clearly. Okay, so let's try this again. And actually, I'm going to comment this out because I wanted to show it to you without that there. Okay, there we go. So we have this dragon. You can see that it's fairly far away. I think I pushed it to like 10 far back or something. If I go back up here and I change it to 1, and I run it again, you can see that that translation is going to dictate where it is in the space, and then you can see that we have this silhouette. And right now it's because the lighting isn't there. Now you have a lot of options with the lighting. You can set the light position and the light color and all these kinds of things, but they have this nice default 3-point lighting. So if I enable the default lighting, watch what's going to happen. Okay? So then we can get some of these things, and you can see the 3-point lighting, there's 2 lights. If I were going to draw this out, there'd be a light from here that's the primary light. There's a light that's kind of coming from the side right here that's a secondary light, and then you have this rim light on the back that's back behind the scene. And you can see that it gives us these areas, especially where it's totally dark, so that you can see the rim is just a little bit lit.
So it's like film.
It's exactly like film. I mean, your graphics borrows a lot of the ideas from film. So how did we get this thing to look a little bit better? Well, how would we do some kind of animation in this case? Like if we wanted to move something around, let's just try to get it to spin around. So if I go up here and said float rotation, we'll set it equal to 0.0 or something like that. Then inside of update, I could say rotation plus equals 0.01 or some small amount. Okay? At this point, I've just changed one variable, but what do I really need to change?
The whole matrix.
Which matrix?
The
The model matrix. So watch what I'm going to do. I'm going to say math, I'm sorry, model? Yeah, there we go. Model gets matrix.identity. So I'm going to, nope, identity. So I'm going to wipe out what was there and start from scratch. And that's disturbing to a lot of people, but it's okay, right? And then I'll say model times equals matrix dot create rotation y. Okay? So what's happening here, rotation. What's happening here is that we started with this matrix identity, and then we said we're going to multiply that by a rotation matrix. So what is the model matrix now? It's actually rotated around just a little bit. Now, if I do this, you're going to be disappointed.
Oh.
What do I see? I am inside the dragon, which sounds like a good movie or something like that. But why am I inside the dragon?
You didn't transform it.
Because I didn't translate the dragon after I rotated it. Does everybody get that? So watch this. How am I going to do this? And you can also see, if you look closely, the clipping planes in action, right? So we could change those things as well. But watch this. If I then say, you know what, I want a translation also, model times equals matrix dot create, whoa. Let's try that again. Create, create translation, there we go. Okay, and we'll do the same thing, 0, 0, -1. And if I run it again, now we get something like this. Right, but think about what's going on. We're always starting back at the identity. And then we're saying, okay, rotate it a little bit and then translate it. Okay, back at the identity, rotate it a little bit more and then translate it. We're always starting from scratch every single frame that you see here. Now watch what I know a lot of you are going to do. In fact, let's push it back 2. Right, because it's there. Okay, so that's pretty good, right? Now watch what we're going to do. What if I did this? Take this out of here and paste it there. I reverse the operations. What's going to happen?
It's going to be going around the camera.
You have an orbiting dragon. Yes. It'll come back. Don't worry. Like the timing there was great. Once it was going.
How would you get the user to solve its rotation?
How would you get? That's a great question. How would you get the user? Like if you wanted to be able to key left, key right, all
Base
that.
the rotation off that?
Well, should we do that real quick?
Yes.
Okay. Should I change this back?
Yeah.
Okay. The reason that I say this is because a lot of people think this way. You think I want to translate it first and then I want to rotate it. But if you do that, the operations are actually backwards in matrix multiplication. So you have to be a little bit careful. Okay. So we now have this. Somebody said, well, what if we wanted to bind keys to be able to do this? Well, what would that look like? If keyboard.getState.isKeyDown keys dot, let's say A, then what will we do? That. Else if keyboard.getState.isKeyDown keys dot D, then what are we going to do? We'll borrow this statement right here and say minus equals. And if I were to run it now, what am I going to see? Static dragon, right? Until. Okay, it's still going around. I'm still holding the key down, right? Here, let's get it back there. Okay, so here's our friend, and then see, so I can steer it that way and steer it that way.
So that's how you would move around the world.
Well, how would we move around the world?
That's where you change the view matrix.
Let's have that discussion again because this is what you're tasked with doing, right? Yes. What about the speed he rotates? Change the point 1 to point 2, right? And it doubles the speed. But how would you move around the world? Because I don't want the dragon. Let's say that we've got this museum experience where everything is static. Nothing moves in the museum other than you. What would you do?
Change the view matrix.
Have a list of.
You would change the view matrix. You would say everything's going to have its translation, and it's never going to change for the life of that. But that view matrix is constantly being updated. Now, here's the trick to the assignment, right? With a view matrix, you can keep the old one, right? So let's say that my view matrix right now is the identity, and I want to walk forward. So watch what I could do. I could say take the old view matrix and multiply it by a little bit of a translation. Let's say 0.1 translation this way. So now I'm here in the next frame. Then what I can do is I can keep that old matrix, the one that I'm currently using, multiply that by a little bit of a matrix translation, right? And I'm going to keep doing this, and I'm going to keep doing this. Now watch why this is cool. Because what happens if the user looks a little bit to the right? And I'm off at, let's say, a 37.94 degree angle. Okay? And so that's what's currently, my view matrix says I've got a rotation that's going along this way. If I do a translation at this point, what's going to happen? I'm going to move along the way that I'm currently facing. Here's what I know a lot of you are going to do, and you're going to be flooded in my office the day the assignment is due, I can guarantee you. You're going to try to keep separate X, Y, and Z positions for the camera, and separate rotation along the X, Y, and Z and everything. You're going to try to do this, and then you're going to figure out real soon that if you are at this 37-degree weird kind of nonsense, how are you going to change your X and Z position in this world based off of 37.9?
Just
With trigonometry.
Trigonometry, which is great. Knock yourself out with sine and cosine all day long. But you don't want to do that. You just want to say everything is going to stay in that view matrix. And if you already turn this way and you're facing up this way, fine. If as soon as I say I'm going to translate, multiply by a translation matrix, I'm going to go up in that direction, guess what? You have a flight simulator. He said, my people need me. So
I must go. My people need me.
okay, so that's what you do. If you want the character to move around, realize the character's not really moving around, like the player's not. But you're going to change that view matrix, and if you do it in this way, you can do kind of whatever you want to do. Does that make sense? So that's your code of the day.
So, how detailed of a tutorial are we going to get along with this?
That's a great question. So how do we know all of this stuff? Well, you can read this, but notice that it says 3D tutorials. This is where I learned how to do 3D in XNA. It's relatively, so there's not much more than what I've just shown you to be able to do what you have to do. Okay? So you can see there's also 2D tutorials, there's input, there's all sorts of interesting things, but I've linked to the 3D side of things. Go through this. Take the 30 minutes out before you just dive into this code and say, Jeff, I don't know what's going on. Read this. And it's going to walk you through, and by the end of that, you're going to have a ship that's moving across the screen or something like that. Okay? So that's a great resource. There's no reason for me to redevelop another tutorial when that's perfectly fine. Yes?
So with like third-person games, it moves both camera and the model.
Okay, so if somebody asked you about a third-person game, how would you do that?
Well, you just have the model set in front of the camera and it move the same way.
Well, they both have the same matrix.
When you
Remember, it's okay. Whether it's first-person, third-person, is there a second-person shooter? I don't think there really is. But anyway,
Oh yeah.
we'll talk later. We'll talk later. We're going to run out of time.
There is a second.
But think about it. Even if the camera's way up here and you've got this third-person perspective, is anything different?
no, you just have to use the animation.
You just change the translation and the rotation of the camera. That's all. All of the concepts that we just talked about are still valid, whether it's first-person or third-person. Doesn't matter. But you're now getting into the whole matrix and seeing how these things are actually working together. Okay? What is it, 521? So let's kind of finish some of this stuff out here. Okay, we talked about orthographic and perspective. I'm going to skip over that for now. Let's talk about some of these other concepts real quick. In graphics, a lot of times you work with buffers. Now, what is a buffer in layman's terms? What is that? It's a chunk of memory. Okay, that's all that it is. And so we store the frame, the thing that's been rendered. That is just a chunk of memory that is then displayed out there to the everyday user, right? So we have a frame buffer, we have a back buffer. Now watch what's going on. If you see here, and I don't know why we picked a toilet picture. It was just like the first thing that popped up in Google. But notice that there's a problem with the toilets.
They're torn up
Why are they torn?
because they tried to move from the top down.
Because it's the way that you're drawing. Sometimes when you see this video tearing, it's because it's drawing it at the same time as it's being shown. Right? So you can actually humanize fast enough to be able to see this thing drawing. You know how they overcome that? Double buffering. Do you know what double buffering is? They alternate the buffers, which means that we understand buffers, right? So they're going to say, okay, fine, here's what the user is currently seeing. Here's where I'm going to draw. So they're drawing the next frame over here, okay? And then what they say, frame is ready to go. What are they going to do? They're going to say, hey, user, don't look over here anymore. Now look over here. Great. So now the user sees that. Then what can we do over here? We can wipe it out, and we can draw the next frame while we're still looking at the old frame. That technique is called double buffering. And when you see it, it gets rid of all of this jittering, all of this tearing, all of this flickering, all that kind of stuff.
What about triple buffering?
Triple buffering, we're not going to talk about.
It's the same thing.
That's like, well, you get, linear filtering, bilinear filtering, trilinear filtering, we're not going to talk about those kinds of things. Okay, there's also something called the depth buffer. right? So when I start pasting all of these pixels, imagine we have a bunch of these things that overlap. How do I know which one to draw? Think about it, because if I have, let's say, 850 trillion things here on the screen, chances are you've got two triangles that want to share that pixel right there. Which one do I draw?
The one that's closest to
The one that's closest, okay? This is different than the way that it used to be with the painter's algorithm. What do painters do? They paint the background, right? And then they've got this background and then everything on the foreground. That's not how it's done. You don't sort anything in computer graphics, right? You rely on the Z buffer or the depth buffer, and then whatever pixel is closest is the one that wins.
We cheat, we don't do it the rendering.
It's not cheating. It's cheating. Right? We also have a stencil buffer, and this is good for when you try to draw something that's not square, or rectangular, I should say. And so here's an example, right? If you look at the rear view mirror, I can draw everything in rectangles without any problem, but how do I draw a curved kind of thing? I can actually overlay this mask. And so I can say, you know what, I don't want you to draw particular regions. That's called the stencil buffer. Okay? Aliasing is best shown here. If I wanted to draw this triangle right here, what would I get? This. In fact, I used to see this a lot of times in old flight simulators. You'd take off, and everything would be flat, and you'd see the horizon. The horizon was perfectly flat. And then what would happen?
You turn a little bit.
You'd turn a little bit, and then you'd see the world split in half. Oh, my God! And it would be this kind of thing. And then it would get worse and worse, and you'd see all these dragging. That's the way it really used to be, guys. Has anybody seen the retina displays?
Yeah.
No, they're nice. That's all I'll say. I have one in my office. Okay. Anyway, so what do? We try to anti-alias these things. And what is anti-aliasing? It's getting rid of all these little jaggies so that I try to make some of these things, instead of being purely white, purely black, I try to smudge them a little bit so that it's like a dark gray, light gray, and it makes a nice kind of effect. Okay, transformations. I think everybody knows translate, rotate, and scale. Yeah, I know. It's okay. Wireframe rendering. Why do they call it a wireframe rendering? You see all of the lines without the faces, okay? And then we have two things that people always confuse. We have hidden surface removal, and we have back face pulling. And let me explain what these things are, because people confuse them all the time. Hidden surface removal says I want occluded objects to not be visible. What does it mean to have an occluded object? It's behind something. So how do we do that? We already talked about it. The Z buffer. That does it for us automatically. So if we have hidden surface removal, that means that something that's behind something else should not be visible. That's what the Z buffer does. If you don't turn depth testing on in OpenGL, you're going to see the weirdest, trippiest stuff. You're going to see stuff that's like, what the heck is that? And the dragon's intestines are going to... No, it's not really that. Okay? And then you have backface pulling. Okay? Now, what backface pulling assumes is that you never want to see the inside of a model. Is that always true? Not always true, but think about it. If somebody's head is there, in fact, I did this in Borderlands. So I was spotting Mothrack. If you know what Mothrack is, giant, how do you say rack? It's just a giant rack, right? It was flying down, and you kill it, and it's so big that we went up to it, but there was no boundary collision, anything there. And you could walk straight into the dragon, and what did I see?
Nothing.
Nothing other than occasionally there were some parts that were facing. So they're assuming in backface pulling that if a triangle is facing away from the camera, there's no reason to render it. Why is that such a good thing?
So you don't
It's fast, right? You're saying, you know what, this triangle does not need to be drawn because it's facing away from the camera. I only want to see, if the camera's facing this way right here and the triangle's facing this way, I want to see it. If it's facing this way, it's the back side, I don't want to see it. It doubles the speed. In general, it doubles the speed of your rendering. Okay, so we have backface pulling as an optimization. Okay, here's an example. Right, if you ever are able to see through walls sometimes, and occasionally you can still do this, even in good games. You can walk up to a wall and then you can kind of see through it.
Yeah.
Why? Walls are a box there, right? Think about this. If we take a cube and we kind of stretch this thing out, and we make a wall, and I get really close to the wall, what's going to happen? It's going to get cut off by the near plane. And then what about the other side of the box? Well, that's the back side. Ha-ha! So what can I do? I can actually see into other parts of the dungeon I'm not supposed to be able to see. Oh, it cuts out. Yeah, the whole thing. It's just like that face is gone, and then you can see all this other. So right now you can see if you screw around with the game system, we're on the back side of the stairs, and you don't want to render these things. Okay, some other things. This is not used very often. Solid shading says, you know what? The heck with lighting. Everything's going to be red. You see any lighting here on this cube? No, it's just red. Whether it's the top or bottom doesn't really matter. Okay, versus flat shading says that all of these, the face right here is going to be lit the same way, right? Some of these may have more direct facing towards the light, but you can see the effect there. Okay, versus texture mapping. What is texture mapping? Putting a texture, right, an image onto the geometry. So this is relatively straightforward. You can imagine that we'd have this image and we paste it on each side. Not such a difficult process, but we do that because it just looks good, right? How did I do this effect right here?
Create another cube.
And another cube. In fact, Mario, one of the Marios kind of things, it was one of the, I think Nintendo 64, had the ability to look at yourself in the mirror.
Yeah.
Like you could run by and you could see the other Mario. That was actually two Marios. There was no reflection, no ray tracing. Yeah. This is not ray traced. What is it? It's a cube, doubled, upside down. And computationally, it's way, way, way cheaper to do this than it is to do ray tracing. If you don't know what ray tracing is, I don't care. Okay? Shaders and materials. There are two primary shaders. You need to know these, especially in job interviews, stuff like that. The two shaders that we have control over, these are programmable things. We actually write C-like kind of code in them. We have a vertex shader, and this is responsible for translations, rotation, scaling, shearing, these kinds of things. You've taken this class, haven't you? You took, yeah. And then you have a pixel or a fragment shader. Now, what's the difference between a pixel and a fragment? It doesn't really matter. A pixel is the smallest light emitting speck on your screen. A fragment is a sub-pixel. Do you care?
No.
I don't either. I don't know why they do that, but yes, you can have something that's smaller than a pixel, and you can do that. But these two things, the primary responsibility of a vertex shader is to move stuff around on the screen. The primary responsibility of a pixel or fragment shader is to color the pixels that are on the screen. Okay? Yeah, let's just move on. Okay, we talk about characters. How do we do character animation? Bones. Okay, so here you can see that we have a model. And I think we had talked about this previously. But you have the model right here. On the inside of that, you have a skeletal structure. You will be implementing part of this inverse kinematics, right? You're going to be making this 2D version of this. But what happens is as I deform these bones, the bones are not rendered, but as I deform the bones, they deform the model mesh. Okay? Now, I want you to appreciate it. We talked about this before, but 60 times per second, we start with a character that's like this. We take the bones to figure out what pose that we're in. We translate that thing and rotate it into the world space, and then we put that into the view space. That goes on 60 times per second for every animated character that you have on the screen. If you don't appreciate that, then that means that you haven't seen how bad it can possibly be. Okay? How about this? I'm going to stop at that. Do you know why? Because it's very difficult to pay attention to what I'm saying. I see people like, oh, Jeff, just stop. So we've gone for an hour. You've seen a lot about this. We'll continue this the next time. We only have probably 30 or 40 more slides past this. It's just too much. It's too much to digest. So the takeaways that you should have from this, especially is the coordinate systems, right? What are the coordinate systems that we studied? Okay, the model space, right? What else? The world space and the view space, right? And so we know that we have to go between that. You saw that in the code, right? We had to create those matrices and move that stuff around using that shader. We actually had access to that vertex shader. Okay. Other things that you learned that, when we're dealing with X and A in 3D, it's not too terribly different than doing 2D stuff. Okay. So you can start pulling in all of these things. In fact, if you want some extra credit, start looking at what you can do with that 3D assignment. In fact, somebody, is it you?
Yeah.
You're working in that. How's it going?
It's kind of stagnant.
Okay.
Yeah.
It'll still be interesting to see.
Yeah.
Okay, so I'll open it up to questions. I wanted to leave a couple of minutes because I know everybody has questions about one thing in particular. And it's not about the game day. And it starts with a B and ends with Ezier. Oh, I'm done with that. How many people are finished? Okay, you guys can leave. Yeah. I just haven't done it.
Wait, I actually read
I was counting myself over the weekend when you went over it last Monday. I went home and finished.
Good.
Yeah.
I just deleted my code and started over on my method.
I have a question about it. Just something I haven't exactly read over all of the instructions, but is there anything specific that we need, like what I was planning on doing for the Bezier curve.
Then you need to hang out.
Well, I was trying to ask you kind of about the specifications of it. If it looks and behaves pretty much the same, is that all?
Hang out. If it's a Bezier thing, because you ask it means that other people have that same question. So I would appreciate it. Class is still not over, so it's not. Okay, so the first question goes to the man with the Firefox shirt. And I know there's three, but you.
I was wondering if there's any specific way that we need to code it for the assignment to be considered, all the way down, or just need to look and behave in the same way as the dev.
So what I'm technically grading on, I get this question a lot, right? And that's why I wanted you to hang out and ask it. People say, Jeff, how should I code this? Do I need to have a point, like a Bezier curve generator class? No, because what happens is everybody has their own kind of signature in the way that they code. Some people have great structure, some people have crap structure, but everybody's building and they're in different places, which is also how I bust people for cheating. People are like, oh, there's only one way to do this. No, I know who is copying off of each other in this class because you can look at the way that people structure code, and it is, I promise you, clear as day. That's not a surprise to anybody. So in your case, you're a senior. I'm not dictating anything to you. I'm saying make this thing. Now, what I don't want to see is that your update function has 850,000 lines of code. At least use like common sense and try to push these things out.
I just hide those in that.
Don't just put them in regions and stuff like that. I really want you to use as good a coding style because it's a practice word.
Well, by that you mean, when you're talking about structure, what I was planning on doing was just to have a point class and then essentially have a method within that class.
I'm not going to dictate. I'm not going to dictate how that. Yeah, that sounds good.
Well, I mean, yeah, you're talking about lines. I wouldn't think you would need that many lines of code. I mean, you already gave us the basic math to work with, so it shouldn't be too hard.
Yeah, I mean, the code structure is up to you. So that's other questions.
And would it be bad if we worked with my partner on this?
It would be to the extent that you're telling him how to code stuff. Right, so if you're talking about, like, hey, how did you mess with that vector? It's like, oh, well, you need to break that down. I have no problem with that, but let him do his own code, right? Because there's tons of lessons. Like, if he's really stuck and maybe has a bug or something like that, you can say, no, you're having some difficulty there. This is where your problem is. That's okay, too. But as soon as you start sharing code, you start telling him what to type, those kinds of things, that's, you have to go through that because as soon as you help somebody too much, you've robbed them and they're not as strong as they should be. That's what I'm trying to do is to get everybody a job. All right, other questions? Questions? Where do you stand with the project? Yes.
We have a question. Were you trying to use 2D arrays to draw?
To draw the what?
To draw the room.
Yeah, it's a different thing. I'm looking for, I'll come back to that, but I'm looking for Bezier questions. Your question?
What
I think you're almost done. Yeah. Okay, so if you have no questions, I can give you no answers, so you feel free to leave. Yes. What I would do is to create a separate control point class. Okay? And it's a special one because you can click on it and you can move it. You with me? So it's not like the other little dots that you have on the screen. This one is a movable thing that as soon as you do that and you move it, you need to recalculate all those points every frame. So you may actually call that generate list of points thing 60 times a second. Right? So as you're dragging this thing, it's going to and it's just calculating new points, calculating new points. If somebody could flip on the lights, I would appreciate that. All right, so
Do we necessarily have to use the dot or the curve?
it should behave exactly like the demo. And that's kind of what this other guy was saying, like what structure do you want us to have? It's up to you. No, I mean, I leave it up to you. I gave you some code on the way that I probably would design it.
I mean, the curve is there, but it's not the dot, dot, dot.
It needs to be dot, 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 dot.
Okay.
But if you have the full curve, then just cut down the number of points that you're drawing. So if you're drawing 10,000 points, cut it down to 100, and you're going to see the dot, dot, dot. Yes? Okay. Yeah, it has to behave exactly like that. How do I draw? No. Yep. The dot. Yeah. So, U, S, oh, the mouse? Yeah. Has been clicked. So, and the mouse is on. Oh, on the control handle? Because you know where the mouse is, you know where the control handle is, and you know the width of that and the height of that box. So you should be able to figure out if this X is within the bounds of this X, and if this Y is. Yeah, there's no clever, inside of box function that's there. So just do it manually.
I don't know what to do with this. It ain't mine.
I'm sorry?
I don't know what to do with this. It ain't mine.
Oh, okay. You found the phone.
Mm-hmm.
Okay, I'll take it and I'll give it to upstairs secretary. All right, I'll shut this down real quick. All right, see you. Let's see dashboard.